Hey everyone, in this quick video, I will discuss the all-important compute metrics method implemented in pretty much all large language model fine-tuning or training. So here is the entire code. All these parts I'm just importing the transformer and the related packages, and then my tokenized dataset I am loading from a local disk, and I'm passing the args because actually, this whole code is part of a bigger code base where I'm doing the entire fine tuning. But here the focus is only the compute metric. So you will see this args variable, which is capturing my dataset directory from the arguments. And then my metric is the rogue metrics, which is a very popular metric while doing LLM fine tuning. And token ID, that's coming from my the model that I'm using here, which is instruction code 5P 16 billion. That's the model I'm using here, and tokenizer is auto tokenizer from pre-trained and then passing the token ID here. Now the most important part, which is the compute metric method. So let's go step by step because you are going to use it almost in any of your LLM related training. So this compute metric, this function is actually a helper function to compute the evaluation metrics for the model's performance. It takes as input the model's prediction and the corresponding true level. So here actually I am passing eval preds, which is a tensor, and we will see the actual shape of this tensor in a moment. And from this tensor, it gets preds and labels. That is, preds here are the predictions and labels are the true labels. So basically, this eval pred that I'm passing to compute metric function is expected to be a tuple consisting of predictions made by the model and the true labels of the dataset. This is standard across Hugging Face's sequence to sequence trainer, where the evaluation step returns the predictions and the labels. The shape of these depends on your data and is typically a batch size by sequence length. So the first part here, what it's doing is the first part of the function handles a case when the model's prediction are in a tuple format. It checks if the predictions are in a tuple, and if so, it just uses the first element of the tuple as a prediction. This is typical for models that returns the loss in addition to the actual model output. So the actual prediction would be in the first position of the tuple. And next, it loops through all the predicted sequences and replaces any instance of -100 with 50256. So here, actually, this spreads IDX2 is the actual token ID value. And so this is done because the -100 is often used as a special value in the labels for tokens that should be ignored in the loss computation. But it's not a valid token ID that can be decoded by the tokenizer. On the other hand, 50256 is the ID for the padding token, which will be ignored by the tokenizer.batch decode. And hence we are replacing -100 with 50256. So after decoding, it can be properly ignored because they are not adding anything to the training of the model. And it then decodes the model's prediction here, batch decode this line. So it decodes the model predictions and labels from token ID to actual text. The tokenizer.batch decode method is used for this purpose. It takes a batch of token IDs and returns the corresponding text. And skip special tokens equal to true, this particular parameter passing is for ignoring the special tokens like padding and unknown tokens. And after the decoding, the function post-processes the text using this method, post-process text. So this post-process text is just a util method defined elsewhere in the overall code base. And it's a helper function defined somewhere in the code base. And this function do a few stuff like trims leading and trailing white spaces for each string, and then splits each text into sentences, joining them with new lines, etc. Because the rogue metric used here that we'll be doing in the next line very much. So the rogue metric used here expects each sentence to be on a new line, and those are the kind of things that this post-process text method will execute. So after this, it computes a rogue metric between the decoded prediction and the decoded labels. And as before this line, the metric object is defined with the code right here. Metric, yes, metric equal to evaluate.load, and then you pass a metric that you want to use. Here I'm using rogue metric. And the rogue is a very common metric for evaluating the quality of summaries by comparing them to reference summaries. It returns a dictionary with the results for rogue 1, rogue 2, and rogue L. Each of these is a different variant of rogue. For example, rogue 1 compares unigrams, rogue 2 compares bigrams, and rogue L compares the longest matching sequence of words. And the results of the rogue metric are then multiplied by 100 and rounded to 4 decimal places. And finally, the function computes average generation length, which is the average number of non-padding tokens in the prediction. This can be useful to understand how long on average the generated sequence are. It appends this result to the dictionary of metrics and then returns the final results. So before calculating the mean, this particular line is important here. Let me zoom in. And that's where I am controlling for that the token should not be a pad token ID. And now I just want to give an example tensor data that this method compute metrics will take to show that how exactly it works. So here my preds is one tensor defined by torch.tensor and labels is another tensor. So imagine that you are fine-tuning a language model for sequence generation task like text summarization or translation. Assume you have a batch of 2 samples, each with a sequence length of only 10 tokens, and that's what I'm representing here, that this is a tensor and each of these list is 10 tokens, and each of these numbers actually represent the input IDs or the token IDs of those tokens. So the tuple eval preds would look like this: preds and label, and it would be passed into the compute metric function with this line, that is preds labels eval preds. And that's what we were saying, that eval preds will be a tuple, and from that we are extracting or unpacking the preds and labels, and then the rest of the execution goes on. So in real world, here I just showed only 10 tokens. In real world scenarios, both the batch size and the sequence length would likely be much larger, and the actual tokens would depend on your data and the task at hand. And then few of the parts of the code that I want to talk about because they are like the most important part. And so the first one is tokenizer.batch decode. This method we are using to decode the decode my encoded prediction and labels tensor. So how exactly this works? Let's go through an example. So the tokenizer.batch decode method is part of the tokenizer object provided by Hugging Face's transformer library. It's used to convert tokenized sequences back into human readable text, performing the inverse operation of the tokenization process. When you tokenize a piece of text, the tokenizer converts each word or subword into a numerical representation known as a token. For example, the sentence I love AI might be tokenized into something like a list of 72, 1801, 1809, something like that. And that's exactly what we are seeing in the code right here. So I'm here importing the auto tokenizer from the transformer library, and then I'm tokenizing it, and then I'm getting the input IDs from this hello I'm a data scientist and return tensor pt, and when I print these input IDs, it will give me a list, and each of these are my input IDs. So the tokenizer maintains a mapping from these numerical tokens back to the original words or subwords. Then the tokenizer.batch decode function takes as input a batch of these token sequences. Each sequence is a list of integers, and decodes them into the original textual form. If the skip special token flag is set to true, which we did in this in our function as well, then it will ignore special tokens like padding, start of sentences, end of sentences, etc. And that's what is being done here as well. So see, when I'm decoding when I'm doing this tokenizer.batch decode here and passing these input IDs, I'm getting back my original human readable sentence. So that's the whole job of these tokenizer.batch decode. And next thing we have to really know in depth is this why we are converting these -100 to 50256. I discussed it briefly during the explanation of the code, but let's go through it quickly again, because you will see these all the time in almost all large language model or any language model training or fine tuning. So in this given code right here, a code snippet that is this block right here, -100 is a special token ID that is often used to represent tokens that should be ignored when computing the loss during model training. These might be extra padding tokens or tokens that are not part of the target sequence in a sequence-to-sequence model. During the process of training a language model, not all tokens in the output sequence are always relevant. For instance, we may have padded sequences to a particular length with irrelevant tokens, or we may want to mask certain tokens. In these scenarios, we assign a token ID of -100 to those tokens we wish the model to ignore when it computes a loss. However, when it's time to evaluate the model, the -100 tokens cannot be decoded back into text since it's not a valid token ID. So, before decoding the sequence, these invalid tokens must be replaced with a valid token ID. And that's where this 50256 comes in. The ID 50256 is chosen here because it corresponds to the padding token in the tokenizer being used. So when tokenizer.batch decode is called with the argument skip special tokens equal to true, it will automatically ignore these padding tokens, so they don't show up in the final decoded text. This is why any -100 tokens are replaced with 50256 before decoding the predicted sequence. And now I also want to talk about this particular line here, labels equal to np.where. So what exactly this line is doing, to understand that, first let's quickly check how np.where works. So this is how np.where, the signature of its syntax, that it checks a condition for each element in the array. If the condition is true, it selects the corresponding element from X. If the condition is false, it selects the corresponding element from Y. And that's the kind of thing I'm doing right here. That is, a condition labels not equal to pad token. It checks each element in the labels array and sees that if it is not equal to pad token, because pad token is the padding token, which is typically used to fill in sequences to a consistent length for batch processing. If the condition is true, the label, that is, the label is not a padding token, it keeps the original label. If the condition is false, the label is padding token, that is, then it replaces the labels with tokenizer.padTokenID. So this operation ensures that all instances of the padding token in the labels are represented with the padding token ID specific to the tokenizer being used. This is important for the subsequent decoding of the labels into text, as the padding token will be correctly ignored during the decoding process. And that's why we execute this line before applying tokenizer.batch decode on the labels. Alright, so that pretty much was this video. I just discussed these specific compute metrics method that you will see in all large language model training and fine-tuning. And the sequence of flows, that is the workflows of these method that we saw right here, it will pretty much be same in almost all the cases. Only minor customization may be required depending on your dataset or your training configuration, but still the overall steps will remain just like this. And this is so important because before evaluation of your training, you definitely have to define this method and only then you can do evaluation of your training. Thank you very much for watching. See you in the next one.